Imagine it's Black Friday and your app is getting thousands of users. Suddenly, your server CPU hits 100%. Then, request starts failing. And finally, your system crashes. Now understand, this is not just a code problem. This is a system design problem. In the last video, we saw why system crash when traffic increases. Now, the question is, how do real systems handle thousands or even millions of users without crashing? Let's start simple. A user sends a request to a server, the server processes it and sends a response. This works fine when traffic is low, but as more users comes in, this single server starts getting overloaded. It becomes a bottleneck, and eventually the system slows down and crashes. So instead of relying on one server, we add more servers. In engineering term, this is called as horizontal scaling. Instead of building a bigger machine, we build a fleet of machines working together. But this creates a new problem. Who decides which request goes to which server? This is where a load balancer comes in. A load balancer sits in front of your servers. It receives all incoming requests and distributes them across multiple servers. When a user types your URL, DNS resolves it to the load balancer's IP, not the server's. The load balancer is the only entry point your system exposes. Remember this. To the user, your system looks like one website, but in reality, it's multiple servers working together. Think of it as a receptionist. It receives requests and directs them to the right server. Here's what happens in a real system. A user makes a request, DNS resolves it to the load balancer, the load balancer receives the request, then it forwards that request to one of the available servers. The load balancer has a public IP, but the servers are inside a private network. These servers are not directly exposed to the internet. Now think about this. We solved the problem of a single server being overloaded. But where can the bottleneck occur now? It could be the load balancer. It could even be the database. Any component that handles all the traffic can become a bottleneck. Systems don't fail at one place. They fail at the weakest point under load. In this video, we'll focus on the load balancer. We'll cover the database in a separate video. So what if the load balancer itself becomes a bottleneck? Just like before, we scale. We can add multiple load balancers. There are different ways to do this. In an active passive setup, one load balancer handles traffic, the other stays on standby, ready to take over if the primary fails. In an active setup, multiple load balancers handle traffic at the same time, often distributed using the DNS. We'll go deeper into these setups in a separate video. Once a request reaches the load balancer, how does it decide where to send it? There are multiple strategies or algorithms: round robin, least connections, IP hash, and more. Each of these has its own pros and cons. Let's understand one simple approach. Let's go with round robin. This is the simplest form of distribution. Requests are assigned sequentially. The first request goes to server 1, the second goes to server 2, the third goes to server 3, and the cycle continues. It assumes all servers are identical and all requests are similar. In real system, that's rarely true, but it's the perfect starting point. In the next video, we'll go deeper into how databases are designed to handle scale and support these kind of system. Because once you solve one bottleneck, the next one appears. So the question is, how do we scale this? Detailed notes for this video are available on GitHub, link in the description. See you in the next one.